pumping lemma for irregular languages was introduced to me as something that was beautiful, and once you understand it, it really is. But it seems to be something many students do without knowing what's going on, or just simply don't understand how to use it, and skip over these questions in an exam when they can be a lot of easy marks to pick up. From my experience, this is because lecturers tend to skip over some steps, assuming students will be able to make the intuitive jump. Now I'm here as a student to teach students. First, it's important to understand what the pumping lemma can and cannot be used for and how to use it. You can follow the timestamps in the description below to skip over this introduction and to move on to the warped examples. However, I would strongly recommend you listen to this whole thing for two reasons. One, it's about when to and when not to use the pumping lemma. This is something many students often lose marks on. And two, even if it is something your lecturer or the other tutorials have mentioned, it is something students typically forget. The pumping lemma is a proof by contradiction method. Therefore, we can use it to prove that a language is not regular. We do this by first assuming a language is regular and then showing that the properties of a regular language does not hold when we pump up or pump down, and thereby finding a contradiction to the initial assumption. If in an exam, you're asked to prove that a language is regular, showing that the properties hold for when we apply the pumping lemma to a word in that language is not enough to prove it. In this case, you will need to find a regular language or grammar for the given language. To prove a language is not regular, we can use a constant k for the number of states as a variable, meaning we do not assign a fixed value to k. We can use this variable to find a string that is greater than or equal to k in length. For this word, we then construct a pumped word that is not part of the language and thereby prove by contradiction that the language must not be regular. We cannot assign a value to k because we don't know how many states the automaton has. Remember, there can be several different automatons that describe the same language. We leave k as a constant to be able to argue that no matter what the value of k is, there can never be a case where such an automaton exists for the given language. So there's no possibility for the given language to be regular. The general idea behind the lemma is, given a non-deterministic finite automaton, so we know there is a finite number of states. If there are k states, which may contain loops, the minimum length of any word x, which is a word within the language of the automaton A, would at least be the number of states k or longer. For such a word x, you must be able to split this word into three subwords, u, v, and w, such that u is the first part of the word, v is the second part that contains the loop, and therefore can be pumped up or down, and w is the end of the word. The length of the first two subwords, u and v together, must contain the first k letters or less of the whole word x. The final condition is that the middle subword v, which will be pumped, has to be at least one alphabet long, meaning v cannot be an empty word. If the automaton A did indeed describe a regular language, then pumping the subword v would construct a new word that should also be a word in the language the automaton A describes. This means raising v to the power of I would follow the properties of the language. Note that I can be any natural number including 0. Now, in the word composed of u, v, and w, v is raised to the power 1. U, v square, w would mean we pumped the word and looped over a state twice. U, v to the power 0, w would mean we pumped down and skipped the loop altogether. To prove that the automaton and the language of the automaton is not regular, we must first assume that the language is regular. We then have to find a long enough word x that is in the language L. What this means is that we have to define the word x in terms of k. The next step is to split the word in such a way that the first two subparts have to be within the first loop. The middle subword has to be at least one alphabet long. Finding a suitable word and splitting the word into its subpart takes some practice, but the more questions you practice, you'll get a better hang of it. And I'll leave 2 questions with you to answer for yourself. There will be another following video which you can use to check your answers, but make sure you do have an attempt first before you check them. Remember, learning cannot be done passively. You have to actively take action. Make sure you do the questions yourself before you have a look at the answers. Here is the first example. Consider the following language, a to the I, b to the I, where I is greater than or equal to 1. This is essentially a block of A's followed by a block of B's of the same length. Assuming this language is a regular language, there will be a finite automaton to describe this language, with k states. Now, to choose a word x, we could say a to the power k, b to the power k is a word in this language. If we imagined an automaton for such a word, the first loop would be after the first a. This word x is greater than k in length because it has 2 blocks of length k. Now, if we were to split this word into 3 subparts where u and v have to be within the first k letters or less, so the word x, which is a to the k, b to the k, will be split so that some of the KAs and the rest of the Bs will have to be the tailing subword W, so that U will be an arbitrary number of A's and V will be another arbitrary number of A's. So finally, A to the K, B to the K is split into 3 parts, A to the I, A to the L, and the remaining A's, which is the total number of K minus I plus L and KBs. This is how we split A to the K, B to the K into U, V, and W. Here, the original word x is split into u, v to the 1, and w. When we pump up the word once more, we have u, v squared, and w. We now have 2 blocks of a to the l, because a to the l is the middle subword v, which we pumped up from v raised to 1 to v raised to 2. This new pumped word is composed of a to the I, a to the l twice, and a to the k minus I plus l in brackets, b to the k. Now, this is the part lecturers skip over, the expanding, because upon closer observation, you could see what they're doing. However, it may not always be intuitive at first glance. That's how I learned it. I couldn't figure it out and just sat there trying to figure out how the lecturer jumped from point A to point B and finally saw it when I expanded all the indices. When we expand k minus I plus L, we get k minus I and minus L. Negative indices mean that we can divide the A's by a to the L, and a to the I. Simply put, we can cross off a to the I, a to the L with the I plus L in the brackets. After simplification, this leaves us with the new pumped up word uv squared w to be a to the k plus l, b to the k. This word is not the same as a to the k, b to the k. A to the k plus l, b to the k is not a word in the language. This is a contradiction. Therefore, we have proved by the pumping lemma that this language cannot be regular. I hope this explanation was easy to follow through with. If you haven't understood it yet, I'll be going through another example. Even if you have understood it, I would advise you to still have a look at how we solve another example to further grasp the idea. There will also be 2 questions at the end of this video, which I would like for you to have a go at to test yourselves on whether you have understood it. The answers will be given in another video. Consider the following language, XXR, such that X is a word composed of A's and B's. The cleany star means that this includes the empty word. If it were a plus, it would have to be any word over the alphabet A, B that is at least 1 alphabet long. This is essentially the language consisting of all even palindromes. It's all even palindromes because the subword X is attached to its reverse word. The capital R as a superscript means the reverse of the word X. If X has 3 alphabets, joining it with its reverse will give 6 alphabets. If X had 2, joining it with its reverse gives you 4 alphabets. In any case, you will always get a palindrome of even length. A long enough word X that we know is in this language could be X equals a to the power k b followed by its inverse b a to the power k. Again, assuming this language is regular, there must exist an automaton for it, and therefore there must exist some k for this language L. And this word x equals a to the k, b, ba to the k can be split into 3 subparts, u, v, and w. Because u and v has to be within the first k alphabets, u and v has to be within the first k a's. Therefore, again, u will be an arbitrary block of A's less than the length of K. V will be another arbitrary length of A's less than K. W will be the remaining K A's followed by B, B, A to the power K. So u v to the power 1 w is a to the I, a to the l, a to the k minus I plus l, b a to the k. If we pump this word up to get uv squared w will equal to a to the I, a to the l twice a k minus I minus l, b a to the k. We can again cross off a to the I with minus I and a to the L with minus L, leaving us with a to the k, a to the L, b a to the k, which we can simplify to a to the k plus L, b a to the k. A to the k plus L a to the k is not the same as a to the k b a to the k. Therefore, a to the k plus L b a to the k is not in the language. This is again a contradiction, and therefore, using the pumping lemma, we have shown that the language containing all even palindromes x reverse is not a regular language. I hope this video was helpful and easy to understand. As promised, here are the following practice questions. Please attempt to answer them yourself before you have a look at the video with the answers. This is because even if you only briefly see the solution and think, oh, you could have come up with this yourself, you need to allow yourself to let your brain go through the process so you're actually learning and not under the illusion of having learned it. Practicing only helps you. Thank you for watching. Please like and subscribe if this was helpful. Comment if you have any suggestions or requests for more videos like this on a specific topic.